All right, welcome everyone to another, class. In today's class, I'll be dealing with magnetism, and I expect that you pay rapt attention so that we can gain the very best in the class. I'll be sharing my screen now so that we can have a deep dive into this topic. So here we go, magnetism. Let me change this template. Okay. Yeah, magnetism. We'll go quickly into that. And what we'll start by talking about what magnets are, what are magnets, and their properties. So I start by saying a magnet is any material that is capable of attracting other pieces of the same material, as well as pieces of iron. So keep that in mind. I now quickly mention that let me be sure I'm writing the right thing. So iodostone, yeah, iodostone is an ion ore which has the property of attracting pieces of iron substance and is said to be ferromagnetic. If it is attracted by a magnet. So the idea here is that examples, the idea here is that this is the magnet, the iron ore, that acts like natural magnet. Let's keep on talking about what we're talking about. Examples of materials which are ferromagnetic. That is, which can be attracted by a magnet. Iron, cobalt, nickel, and then alloys. Or let's say certain alloys. Let's do that with certain alloys. This class is very straightforward. It's a class where you take notes and then you keep those knowledge because they're important. So substances which cannot be attracted by a magnet are called non-magnetic materials. Examples include brass, wood, copper, glass. Now demonstrating properties of magnets. Number one, the ends of a magnet where the attracting power is greatest, they are called the poles. So the attracting power of a magnet is greatest at the poles. A bar magnet suspended freely in a vertical plane called the magnetic meridian it comes to rest with its axis in the north-south direction. The path which points northward is called the north seeking pole, or some just call it simply the North Pole. While the opposite of that so please keep all of these statements in mind, all these characteristics in mind. It's your duty to reread them, memorize them, understand them, keep them in mind. Like poles, don't worry, we'll give diagrams to express this thing. Like poles of magnet repel, just like in the case of electric charges. Like poles repel, like pole of magnet also repel each other. Why unlike poles attract each other. The polarity of a magnet can be tested. by bringing both poles in turn nearer to the unknown. Polarity of a magnet can be tested by bringing both poles in turn nearer to the known pole of a suspended magnet. Okay. Nearer to the known poles of a suspended magnet. The meaning of this now is that we're saying that if we have a magnet, say North Pole and South Pole here, and then we have another magnet, North Pole and South Pole. Of course, South Pole stuff are entering from the South Pole, and of course from the North Pole stuff are coming out. So it's very easy for them to attract North Pole and South Pole. Like we said, stuff is entering from South Pole. So stuff are coming out from North Pole. So stuff keeps coming out and going to the South Pole to enter. So same here, coming out from here, going here to enter. So that's the idea. Can repeat that again. Coming out of North Pole, entering at South Pole. Same thing here, coming out of North Pole. That's the field line, that's the attraction here. So same thing, coming out of North Pole, entering at South Pole. Coming out of North Pole, entering at South Pole. So that's the idea. So this is more like attraction. This is where we see how we see the concept of attraction coming out of North Pole, entering at South Pole. But if we place the magnet in this order, now this was because we placed the magnet like this, north, south, north, south. What if we place it now such that the north and north, that is north and north, existing here, north and north. I will know that stuff comes out of north and enters south. So what's gonna be happening here is that stuff is gonna be coming out of north, stuff is gonna be coming out of north and going back to enter south. So stuff is gonna be coming out of this north and going back to enter south. Same here. Stuff coming out of north. And when I say stuff, I mean like the feed lines. So coming out and entering south. So this time around, these two things are going to repel. So these two magnets, attraction is here, but here we'll see repulsion. That's how we call it. So you can choose to double the lines just like we did above. So, but that's the concept. Now, let's say if I have an unknown guy, this guy is unknown, and I want to know the polarity. I just bring it near a known magnet, north and south. And if I bring it near like that, what do I mean by I want to know the polarity? I don't know what's here, and I don't know what's here. But when I bring it, I notice that, oh, it is coming. It is attracted. If it is attracted, what does that tell you? From this end. It's attracted from this end. What does that tell you of this end? This particular end. It means it is south, definitely, because north will repel north, but south will be attracted to. But if it is repulsive, this same side, if it is repelled rather, it is repelled means if it's attracted means it is south. Repelled means it is not. So that's the fourth property that I was talking about. The polarity of magnet can be tested by bringing both poles in turn near to the known pole of a suspended magnet. So what you mean by bringing both poles in turn is that after I determine here, I have to turn it and determine here too. So don't just say, oh, it's not out. No, do both and test them with this side. You get? So yeah, that's the idea. So just keep that in mind. So let's write the point. Repulsion, still under point 4. Repulsion indicates similar polarity. Like with the point of comparison. Repulsion means that they have similarity. Then attraction could be due to two unlike poles, or a pole and a piece of unmagnetized material. Attraction can mean two things: that the two poles are, of opposite polarity, unlike poles, or it means that the material is unmagnetized. So we now say that, since attraction gives you two options, repulsion is the true test. Repulsion is the only sure stroke true test for polarity. So let me go to the next subtopic: magnetization and demagnetization. So magnetization and demagnetization. Let me start from magnetization. Magnetization is the process whereby a material is made to become magnetic. It is the process whereby material is made to become magnetic, and it can be achieved through any of the following methods. Magnetization can be achieved through any of the following methods, but I'm going to start with electrical method. And this method is cylindrical coil wound. When you say wound, it's when you wind something, past tense of wind. When you wind something around, like twist. A cylindrical coil wound or twisted with several turns of insulated copper wire is connected in series with a 6 or 12-volt electric battery and a switch. That cylindrical coil. So this is a magnet now already. Just by setting up a cylindrical coil twisted or wound with several turns of insulated copper wire and connecting it in series with 6 to 12-volt battery and having a switch. So that's a magnet. So the solenoid, hold on for a bit. The setup is not complete. The steel bar, okay, let's see. Okay, the coil, hold on, just continue. Just you're gonna look at the full picture at the end of one. This coil is this coil, that is the cylindrical coil. This cylindrical coil is called a solenoid. So a steel bar. So after you have this setup above, a steel bar is now placed. It's placed inside the coil, and the current is switched on for some time. As I say, you should hold on for a bit. It's not a magnet yet. So now we've placed a steel bar inside the coil and turned on the current for some time. So what we now have now is that on removing the steel, so by the time we remove the steel, so by the time the steel is removed, it would be magnetized. So that's just a process of magnetizing steel. So you use all those things. So you set up all these things, the coil and all of that, twist it, and then you have a steel bar. So I'm assuming that, I have coil like this. I place a steel bar in there, connect it to a battery. Understand? And I complete the connection. So this is a simple setup. So if I on this current, they say we have a switch. So let me say this is my switch. So if I on this current, I on my current, I allow current to flow. After some time, this particular steel bar, so there is a steel bar here, steel bar, this coil, this is the coil. It's not just normal coil, we call it solenoid. Solenoid. Now these are connecting wires. This is a battery. That guy is battery. And this guy is switch. So let me give you some time to take it on that diagram. Remind you the concept, passed across that knowledge. Keep it in mind. So take some time, draw the diagram. So keep that in mind. The next method we are looking at, we just looked at electrical method. We'll go straight into something called the single touch method. And what happens here? A steel bar is struck from end to end several times. So you have a steel bar stroke from end to end several times in same direction with a known pole of a magnet. Between successive strokes, pole is lifted high above the bar. Otherwise, magnetism will be weakened. Magnetism already induced will be weakened. So we're going to state that a major disadvantage is that this method uses magnets in which one pole is nearer the end of the bar than the other. So the concept is that we have a steel bar, and we say we stroke from end to end several times. Let's say this is a magnet now, and this is north and south. So we move this platform, move it like this and like this on the surface of this steel bar. Move it from end to end. Move it, keep moving it several times in the same direction. Oh, that means we're not even free to move it like this and like this. So it's more like, let me re-establish my diagram. If I start from here, so this is my steel bar. If I have my magnet, let me draw it in green. If I have my magnet right here, and north and south. I keep moving it like this only. And so I don't touch it again. I just bring it back to this point and move it again. So bring it back to this point and move it again in that same direction. So I'm not moving it to and fro. No, I'm moving it, come to one direction, stroke it. So the idea is that between each successive stroke, you leave the palm high above the bar. Otherwise, you destroy. So when I move it first time, as I'm moving it now, I'm not like putting the entire stuff on this. I'm not also putting this one down. No, I'm using one hand to hold this place and stroke it, move it there. So then I lift that side. That's just single touch method. So only that one side I will touch it. I'm not putting this other side down, so that's not happening. So now that part is lifted. So lift it above. So I just stroke like that and I'm able to get what I need. So then the third method is called divided touch. Divided touch method. And what happens in this method? Here, the steel bar is stroke from the center outward with unlike poles of two magnets simultaneously. So the idea here is we have our steel bar, and as we are stroking with one magnet from here, let me go back. So stroking with one magnet from here, we're stroking with another magnet from here. This one has north, south, and this one has north, south. So you're stroking this one in this direction, stroking this one in this direction. Stroke like this in this direction and come back again and stroke again in this direction. So stroke like this, and come back to the starting point and stroke again. So keep going like that. Before you know, I didn't even mention what this side will attend. So by the time we are done, this side will be north, this side will be south. So but in this case now, this side is going to be north, and then this side is going to be south. So how are we moving? So in this case, move like this, then come again, move. So this case, move like this, then come back again, and move and keep repeating it. So yeah, move. So let me change that to green. So move like this, come back, move. So yeah, move like this, I come back. I keep repeating the process. So same with this one, I move like this, I come back, and then I keep repeating the process. So that's double touch, that's just the difference how they look diagrammatically. Then hammering in the earth field is another way of creating magnet. hammering in the earth field. So magnets can be made by hammering red hot steel bar and allow it allowing it to cool as it lies in north south direction. So put that in mind. And the last one is what I'll call number 5, induced magnetism. What happens here is when a piece of unmagnetized steel is placed either near or in contact with a pole of a magnet and then removed. So when a piece of unmagnetized steel is placed either near or in contact with a pole of a magnet and then removed, it will be magnetized. So it's as simple as that. So this process is called induced magnetism. So, and the idea is that the induced pole is always opposite to the inducing pole. So whatever is responsible for causing the induction at that point, that induced pole will take the opposite sign. So let's go straight into what the magnetization is. We've talked about magnetization. So what is demagnetization? Now does that process occur? This is a process whereby a magnet is made to lose its magnetism. And you achieve that by the methods include when you make something lose its magnetism. The methods include electrical, and this method is solenoid. Let's say the magnet is placed in a solenoid through which excuse me, an alternating current is flowing. So once you have an alternating current flowing, that's the end. So it says magnet is placed in a solenoid through which alternating current is flowing. Then look at the idea. The solenoid is placed with axis pointing east-west. So after a few seconds, you now remove the magnet. The magnet is withdrawn out of the solenoid to long distance away. So this particular method is the most efficient. The most efficient way of demagnetizing a magnet. Keep that in mind. There is another method called this is the electrical method that we just talked about. There's another method called mechanical method. And in this method, the magnet is hammered. You hammer something, is hammered hard when it is pointing in east-west direction. And there is a heating method. And this method, application of strong heat, that's all. Demagnetizes a magnet. Types of magnets, temporary and permanent. So for temporary and permanent magnets, let's just talk about this. Temporary permanent magnet. So after this, we'll talk about magnetic fields briefly, and then that will be it for this class. So before we talk about temporary and permanent magnets, we must acknowledge that steel is much harder and stronger than soft iron. So steel itself is an alloy of iron and carbon. And steel is the stronger steel produces, let's say like this, steel produces permanent magnet because it hardly loses rather its magnetic property. Or you can say it hardly loses its magnetism. Let's just put it as magnetism. So it hardly loses its magnetism. It is therefore used in compass needle. So like in making, let's say in making permanent magnets like compass needle. So that's the idea. So we, on the other hand, we can say soft iron, which is pure iron, is easily magnetized but loses it easily. You can easily magnetize it than steel, but then you can also lose that magnetic property, but readily loses it. And is thus used where magnetism is required for short time as temporary magnet. And that's in materials like electromagnets. So keep that in mind. So soft iron related to temporary magnet, steel related to permanent magnets. Keep that in mind. Let's talk about magnetic fields for a bit. This is the space surrounding magnets. Where the magnetic force exerted by such magnet can be felt. So it's a space where we feel magnetic force. It is a vector quantity. So all fields are vector quantities. Electric field, magnetic field, gravitational field, they are vector quantities. And it is represented by magnetic lines. So most of them we call it magnetic field lines. It is very important to note that the direction, I'll make some points and define some terms before we call it a day. Direction of the magnetic flux at any point is the direction of the force on a north pole placed at that point. So we must also know that in the neighborhood of two magnets placed close together, there exists a field in which the direction of the magnetic flux changes rapidly in a confined space. The neighborhood of two magnets placed close together, there exists a field in which the direction of magnetic flux changes rapidly in a confined space. So this magnetic flux, so it's just telling us that magnetic flux exists when two magnets are close together. The magnetic flux can be obtained by using ion filings, but let's say ion fillings, yeah. So let's quickly define a term like magnetic meridian. Magnetic meridian at any place. It's a vertical plane containing the magnetic axis of a freely suspended magnet at rest under the action of the earth field. The geographical meridian at a place is a plane containing, so this is a separate thing, the place and the earth's axis of rotation. So take note of those definitions. They can show up in your theory. Final thing we'll talk about before we call it today, the angle between the magnetic. This can come out in multiple choice, OBJ, and geographical meridian is called magnetic declination. So this is between magnetic and geographical meridian. It's called magnetic declination. While the angle between the direction of the Earth's magnetic flux and the horizontal is called angle of dip or angle of inclination. So this is what we'll call it a day in today's class. And I will see you in the next.